Have you ever looked up at Orion and felt like one of its stars was staring back? There's a bright, reddish point on his shoulder called Betelgeuse, and in cosmic terms, it's a ticking bomb. Not in a scary way, but in a this star is living its final chapters kind of way. One day, it will explode as a supernova so bright it could rival the moon. What happens then? Does Earth notice? Do our nights change forever? Or does the universe shrug and keep moving? Tonight, we're going to slow down and unpack what it really means for a nearby star to die in such a dramatic way. If you enjoy this kind of quiet trip through space, a simple like and subscribe helps more people find it. Settle in. Let's talk about Betelgeuse before it blows. The star known as Betelgeuse is classified as a red supergiant. This is a very specific and very significant category. The red part of its name indicates that its surface temperature is relatively cool compared to many other types of stars, including our own sun. But the supergiant part describes its truly massive scale. The relationship between its temperature and its size is key. Precisely because it is cooler, it must be enormous to shine as brightly as it does. Its diameter is difficult to comprehend in human terms. Let us use a more familiar framework, our own solar system. If we were to remove our sun and place Betelgeuse at its center, the physical surface of this one star would extend past the orbit of Mercury, past Venus, past Earth, and past Mars. Its vast, tenuous outer atmosphere would reach beyond the main asteroid belt, perhaps even approaching the orbit of Jupiter. Our entire inner solar system would be consumed, existing only as coordinates inside another star. This colossal object is located approximately 700 light-years away from us. This distance introduces a fundamental concept in astronomy. A light-year is the distance light travels in 1 year. Because Betelgeuse is 700 light-years away, the light we see when we look at it tonight did not leave the star tonight. It left the star 700 years ago. We are observing Betelgeuse as it was during the 14th century on Earth. We are, quite literally, looking 700 years into the past. Even at this immense distance, the sheer size of Betelgeuse makes it one of the most prominent objects in our sky. To the naked eye, it is the 10th brightest star visible from Earth. However, if our eyes could see in the infrared spectrum, which is a way of seeing heat rather than visible light, it would be the single brightest star in the entire sky. You can find it easily, marking the left shoulder in the constellation of Orion. When you observe it, you may notice it is visibly redder than the surrounding stars. You will also notice that it twinkles or scintillates a great deal. This is partly due to Earth's atmosphere, but it is also because Betelgeuse itself is not a stable, steady point of light. Its surface is a violently boiling, convective mass. This visible instability points to another special fact about Betelgeuse. It is a star that is nearing the end of its life. It is likely to explode in a supernova at any moment. Now, it is critical to understand what any moment means in astronomical timescales. This phrase, used by scientists, means it could happen tomorrow night. It could also mean it will not happen for another 100,000 years. Our understanding of stellar life cycles puts it in this very wide but very certain final window. To understand why it is guaranteed to explode, we must understand how such a massive star lives. Stars in their adulthood, a phase called the main sequence, are powered by the nuclear fusion in their core. Their primary function is to convert the most basic element, hydrogen, into the next element, helium. This process is a battle. The star's own immense gravity is constantly trying to crush it, pulling all of its mass inward toward the center. But the fusion in the core creates an enormous amount of energy, light, and heat, which pushes outward. This outward radiation pressure is what combats the effect of gravity, keeping the star balanced, stable, and in a specific volume. Our sun is in this stable phase right now, but this process cannot last forever because the fuel is finite. Eventually, the star will run out of hydrogen fuel in its core, having converted it all to helium. When this happens, the fusion process stops. The outward pressure, the force fighting gravity, suddenly vanishes. Gravity wins. The core, no longer supported, collapses under its own weight. For a star of average size, this is the end. But for a star as massive as Betelgeuse, this collapse is actually a new beginning. The compression of the core becomes so intense that the temperature and pressure skyrocket until they become high enough to trigger a new fusion reaction. This time, the star begins to fuse the helium it just created. It converts helium into heavier elements, like carbon. This new fusion cycle reignites the outward pressure, stopping the collapse. But this new energy source is hotter and more intense. It causes the star's outer layers to expand dramatically by hundreds of times. This is the moment the star leaves the main sequence and begins the red supergiant phase of its life. The star's interior begins to resemble an onion. When the helium runs out, the core collapses again. It gets even hotter, and it begins to fuse carbon into oxygen and neon. When the carbon runs out, it collapses again and begins fusing oxygen into silicon. This process repeats, with each new fusion cycle creating heavier elements happening faster and faster. The star's core becomes a series of concentric shells with the heaviest elements at the center. At the very center of it all, the silicon-burning phase creates the final element, iron, and iron is the end of the line. For all the previous fusion cycles, the process released energy. Fusing hydrogen, helium, or carbon created a net gain of energy, which supported the star. Fusing iron is different. The process of fusing iron atoms together does not release energy. It consumes energy. It takes more power to do it than the reaction provides. When the core of Betelgeuse has been converted predominantly into iron, the furnace at the center of the star turns off permanently. With no fusion to create outward pressure, there is nothing left to combat the effects of gravity. The star undergoes a final, complete collapse. The outer layers of the star, suddenly finding no support from below, begin to fall inward at speeds approaching a quarter of the speed of light. They slam into the impossibly dense iron core and rebound in a catastrophic explosion. This is the supernova. That is where we are with Betelgeuse. We are awaiting this final collapse. Whenever it does explode, it will eject its entire atmosphere, all those layers of oxygen, carbon, and helium far out into space. From our vantage point on Earth, it will be an unimaginable spectacle. It will be visible in our sky for a good 2 to 3 months before it begins to dim again. It is predicted that it will become perhaps as bright as a full moon, meaning it would cast shadows on the ground at night. It would be so bright that it would be easily visible during the day. It is important to emphasize that Betelgeuse is far enough away that no harm will come to Earth. The radiation and material will be too dispersed to cause any damage. It will simply be the most significant astronomical event in recorded human history. This brings us to something very interesting that has been going on with Betelgeuse recently. It has been in the news. In 2009, it was observed to have contracted in size by 15%. You may have also heard that, starting in 2019, Betelgeuse began dimming dramatically. This unusual behavior led to rampant speculation among scientists and the public. Was this dimming a precursor to the promised supernova? Was the star's internal engine finally sputtering, the light output dropping just before the final collapse? Although this was an exciting idea, it appears, sadly, that this is likely not the case. New data, primarily from the Hubble Space Telescope, has shown that the star itself may not have been dimming at all. Rather, it seems our view of the star was simply obscured by a large cloud of dust that the star itself had ejected. Here is what the observation showed. In September of 2019, Hubble instruments saw a large amount of heated material moving away from the star's atmosphere, specifically from its southern hemisphere. Over the course of the next few months, this material was observed near the star. Then, by December, the star began to dim, especially in that same southern region. The working theory is that this outflow of gas contained heated carbon. As this massive cloud of hot gas moved away from the star's surface, it expanded. As any gas expands, it cools. As this carbon gas cooled, it reached a temperature where it condensed, turning from a gas into solid particles. In essence, Betelgeuse ejected a massive cloud of hot gas that then cooled and formed a vast plume of soot or dust. We lost sight of the material not because it moved away, but because it cooled down and crossed over our direct line of sight to Betelgeuse, blocking its light. At its peak dimness, Betelgeuse appeared about 2/3 dimmer than normal. However, since April of 2020, Betelgeuse has actually returned to its normal, familiar brightness. This tells us that the dust cloud has either moved out of the way, continuing its journey into space, or it is totally dispersed. So, this event was probably not the exciting conclusion to this star's story that many were looking for. Probably no supernovas for a while yet, but maybe that is a good thing. After the event, Betelgeuse will no longer be visible as the familiar point of light on Orion's shoulder. So, next time you have a clear night, find Orion in the sky and have a new appreciation for the red, twinkly star of Betelgeuse. We are observing an object officially known as the spire. This is not a solid object, but rather a towering pillar composed of cold interstellar gas and dense molecular dust. It is located within a much larger formation, the Eagle Nebula, which is well known as a stellar nursery. This term signifies that it is an active region where new stars are currently being formed. The sense of scale in these cosmic images is often difficult to truly internalize. This single pillar of gas stands 9.5 light years high. To contextualize this, light, which is the fastest moving thing in the universe, requires almost a full decade to travel from the base of this structure to its absolute peak. This magnificent pillar is not a permanent fixture. It is in a constant state of transformation. We are witnessing a process of sculpting and erosion on a massive scale. The forces causing this erosion are located just outside the frame of this specific image. Nearby, a cluster containing thousands of very hot, very young, and very massive stars is emitting an intense and relentless flood of high-energy ultraviolet radiation. This radiation is the tool that is carving the spire. The faint, Ethereal haze that appears to surround the structure is direct evidence of this process. This haze is hydrogen gas. The ultraviolet light is so powerful that it heats the gas on the surface of the pillar, causing it to boil off in a process scientists call photoevaporation. The regions that appear dark and opaque, particularly the stalk of the pillar, are not shadows. They are simply areas where the gas is significantly denser. This density makes them more resistant to the ultraviolet radiation, but they, too, are being steadily worn away over millennia. This interaction, this process of destruction, is simultaneously a process of creation. The very same intense pressure from the hot stars that pushes against the pillar is also a mechanism for triggering new star birth, as the shock wave of hot, expanding gas slams into the dark, colder, denser regions of the pillar. It compresses this material. This compression can push parts of the cloud past a critical density, at which point their own internal gravity takes over, causing them to collapse and ignite as new stars. Star formation is also happening deep within the tower itself, independent of the external pressure. In the densest, coldest pockets of the cloud, gravity alone is enough to pull material together into collapsing knots. The small, distinct bumps or nodules visible near the very top of the pillar are evidence of this. While they may appear small in an image of this scale, each individual bump is estimated to be roughly the size of our entire solar system. These are protostars, embryonic stars still gathering mass. They will continue to grow and accumulate material as long as there is available gas in their immediate vicinity to feed upon. The background of the image is filled with more distant gas, also illuminated. The colors seen here are not what the human eye would perceive. They are representations assigned by scientists to understand the chemical composition. The red-orange glow indicates the presence and interaction of hydrogen gas. The distinct blue tint represents the signature of oxygen, which is being excited by the ultraviolet light. We now move significantly farther away, traveling 210,000 light years from Earth. This journey takes us outside of our own Milky Way galaxy entirely, to one of its nearby satellite galaxies, a smaller, irregular galaxy known as the Small Magellanic Cloud. Within this companion galaxy, we find the object NGC 346. This is one of the most dynamic and intricately detailed star-forming regions currently known to science. At the heart of this region, we see an intense and brilliant cluster of young stars. This cluster is surrounded by a jagged, sharp-looking arch, a ridge of dark, cool gas and dust, much like the spire we just observed. A similar process is unfolding here. The powerful ultraviolet light from the central cluster of stars is blasting against this dense, dark structure. This creates a form of stellar wind, a stream of radiation and particles moving outward from the stars. You can clearly see the effect of this wind. It has created wind trails or comet tails behind the denser globules of gas that are resisting the flow, pointing away from the central energy source. This star cluster is also notable for housing the single brightest star yet identified in the entire Small Magellanic Cloud. Next, we observe the Crab Nebula. This object is a remnant, the direct aftermath of a star that ended its life in a massive supernova explosion. This is not a theoretical event. The explosion itself was so bright that it was documented by ancient Japanese and Chinese astronomers who recorded seeing a guest star in the sky in the year 1054. What you are looking at here are the remains of that star, primarily its outer layers of hydrogen gas, which were ejected violently into space. These remains are still expanding outward from the site of the explosion. Barely visible at the precise center of this intricate, web-like picture is the object that was created by the star's death, a neutron star. This is the ultra-dense, collapsed core of the original exploded star. A neutron star is an object of almost inconceivable physics. It contains roughly the mass of our sun, but it has been compressed into a sphere that is only about 30 kilometers across. This particular neutron star is rotating at an amazing 30 times per second. As it rotates, it shoots two highly focused beams of high-powered X-ray radiation out into space, like a cosmic lighthouse. This is the energy source that causes the eerie, bluish glow visible in the inner region of the nebula. When astronomers on Earth observe this central star, it appears to be pulsating rapidly. This is not because the star itself is flashing, but because its rotating beam sweeps past our line of sight sight 30 times every second. We now move to the Orion Nebula. This is a vast region of star birth. The image reveals an enormous amount of activity, housing approximately 3,000 stars in various stages of life, some of which were not even discovered until this particular picture was taken. In the center of the brightest patch of light are the four biggest, most massive stars in the entire nebula. They are arranged in a pattern called a trapezoid and are aptly named the trapezium. The intense radiation from these four stars is what illuminates much of the surrounding nebula. Around these stars, we can observe extremely young stars that likely still possess their protoplanetary disks. One is visible here. These disks, composed of condensing gas and dust, are the raw materials from which planets will form in the distant future. At the top left of the image, we see a single star that is illuminating the surrounding dust, a region designated M43. Elsewhere in the image, we see more examples of dense gas resisting erosion by ultraviolet light and other regions of gas reacting to it. You can visibly see the bow shocks from some stars. These are wave-like structures formed as the star's own stellar wind pushes back against the powerful, oncoming stellar wind from the massive stars of the trapezium. On the left, we see a distinct cavity wall, the edge of the hollowed-out bubble that the central stars have carved in the nebula. Finally, you may notice many dim, red points of light, some of which are just tiny pixels. These are not distant galaxies, but brown dwarfs, sometimes referred to as failed stars. A brown dwarf is an object that forms through the same process as a star by pulling gas together through gravity. However, it fails to accumulate enough mass. Its internal gravity is insufficient to ignite and sustain the nuclear fusion of hydrogen in its core, which is the process that powers our sun. As a result, brown dwarfs are comparatively cool, much less massive, and do not shine brightly. They glow faintly, mostly in the infrared, from the residual heat left over from their formation. The Orion Nebula is the closest major star-forming region to us, located just over 1,300 light-years away. We are looking at the Pinwheel Galaxy, also identified as M101. This object is classified as a grand design spiral galaxy. This is a specific designation, separate from other types of spiral galaxies. It means that its spiral arms are prominent, well-defined, and appear to wrap continuously and clearly around the galactic center. This contrasts with flocculent or patchy spirals, whose arms are less distinct and more broken. This image itself is a massive composite, allowing us to take a detailed journey from one side of the galaxy to the other. The Pinwheel Galaxy is a reasonably close neighbor to our own Milky Way, at a distance of only 21 million light-years. It is also comparable in size to our own galaxy. Its most notable features are those very distinct arms. They contain an unusually high ratio of star-forming regions, which are visible where the colors in this enhanced image are strongest. The brilliant blue patches highlight clusters of extremely hot, young, and massive stars. The pink and red glowing regions are clouds of hydrogen gas, energized and made to glow by the intense ultraviolet radiation from those new stars. This high level of activity means it is a very active galaxy. The spiral arms themselves are waves of density, places where gas and dust are compressed as they orbit the galactic center. This compression is what triggers the collapse of interstellar clouds, leading to the high rate of star formation we observe. Our next object is the Cigar Galaxy, or M82. This is a magnificent example of a starburst galaxy. This term means the galaxy is undergoing an exceptionally high rate of star formation, far beyond what is typical. This galaxy is remarkable for the visible, flame-like plumes of red hydrogen gas being ejected from its core, perpendicular to the galactic disk. These outflows are the consequence of the intense activity within. Young stars are being born 10 times faster in this galaxy than they are inside our own Milky Way. This intense, galaxy-wide burst of activity is thought to be caused by gravitational interactions with its close neighbor, M81. The two galaxies are only 300,000 light-years apart. Because of their immense gravity and close proximity, they exert powerful tidal effects on each other. The gravity from M81 has stretched and squeezed M82, compressing its internal gas clouds on a massive scale. This compression has triggered the galaxy-wide starburst, which in turn powers the superwinds, driving out the red hydrogen plumes. M82 also houses the brightest known X-ray pulsar, called M82X2. In this image, it is the large pink dot near the middle. This object has left astronomers puzzled. It is pumping out 100 times more X-ray radiation than something of its mass should physically be able to produce. There is a concept known as the Eddington limit, which defines the maximum brightness an object can have before its own radiation pressure literally blasts away the material that is falling in and feeding it. M82X2 is violating this limit by a huge margin, and the mechanism is not yet understood. As a comparison, X2's binary system companion, M82X1, which is the pink dot to the bottom right, is a confirmed black hole. Yet, surprisingly, it emits less X-ray radiation than the pulsar. We now turn to Cassiopeia A. This colorful, chaotic object is the aftermath of a star that exploded. It is a supernova remnant. Specifically, it is the youngest known remnant of a supernova explosion within our own galaxy, and it is only 11,000 light-years away from us. Based on its distance and the speed of its expansion, we calculate that the light from this explosion should have first reached Earth about 300 years ago. This is a significant date, as it is after the invention of the telescope, yet there is no historical record of any sightings from any astronomer. This remains a mystery. One hypothesis is that the outer layers of the star were already ejected in the centuries before the final explosion. This shell of gas might have acted as a shroud, absorbing the intense visible light of the supernova and rendering it invisible from Earth. But it is not really known for certain why it was missed. Incredibly, the expanding explosion shell composed of the star's former insides, is still hot. Measured at about 30 million degrees centigrade, it is still expanding outward at a speed of 6,000 kilometers per second. This shell of debris is now about 10 light years across. Our next object is the Lobster Nebula. This is another star-forming region, a beautiful nebula found in the Milky Way at a distance of around 11,000 light years from us. This nebula contains a large number of protostars, which are embryonic stars still in the process of forming. Many are visible in infrared images found within dark disks of gas and dust and shrouded in cocoons of gas that obscure their visible light. This nebula contains a star cluster known as Pismis 24. Within this cluster, one object, Pismis 24-1, was once thought to be the most massive star on record at an estimated 300 solar masses. This would have placed it far beyond the theoretical limits of star formation. However, closer observation revealed that this is not one object. It is actually a multi-star system and is, in fact, at least 3 separate stars. Each of these stars is about 100 solar masses. Even with this reduction in size, though, they are still some of the most massive and luminous stars that we know about, existing at the very upper end of stellar possibility. Here we see NGC 602. This image is beautiful, not just for its shapes and its colors, but also because of the sheer number of background galaxies visible. The reason these distant galaxies are so clear is because NGC 602 is located in a remote part of one of our satellite galaxies, the Small Magellanic Cloud. It is away from the crowded center, in a less dense suburb of that galaxy. This means there are not as many intervening foreground stars from the Small Magellanic Cloud to distort the view or create star fog. This clear line of sight makes the background galaxies easily visible, and it also makes the nebula itself much easier for scientists to study. At the center of the nebula is a cluster of young, bright blue stars whose radiation is eroding the surrounding dust walls and creating the bubble-like shape. This is the final image for this segment, NGC 1672. What we have here is a barred spiral galaxy. This classification is different from the grand design spiral we saw earlier. This galaxy has 2 very prominent arms, which come away from the rest of the galaxy. The one on the left of this image is significantly more prominent than the other. This galaxy actually has 4 arms. The final 2 are not as defined, and they are tucked away inside the main structure. The critical, defining feature is that these arms do not join at the nucleus. Instead, they emerge from the ends of a distinct, straight bar of stars that cuts through the galaxy's center. This is precisely why it is referred to as a barred spiral galaxy. This bar is not just a visual feature, it is a dynamic structure. Its gravity acts as a pipeline, funneling gas and dust from the outer arms toward the galactic center. This funneling action is what is triggering the starburst, an extreme amount of star formation that we observe in the regions surrounding the central bar. NGC 1672 is an impressive 60 million light years away. Black holes are one of the most mind-boggling aspects of space. For a start, they are not actually objects in the traditional sense. They are the result of the extreme warping of space-time. And because of this warping, some truly strange phenomena start to occur around them. Phenomena that will change your perspective of the way the universe operates around you. Some of it is so strange that perhaps you would not believe it was true, were it not for the solid mathematics that back up their existence and properties, and the increasing evidence that the mathematics is correct through observations in our own universe. To understand the universe is to understand the extreme, and there is no object more extreme nor more fundamental to our understanding of gravity and time than the black hole. These are not merely empty voids or caverns in space, as the name might unfortunately suggest. They are objects of immense substance, defined by density so profound that it breaks the rules of physics as we experience them in our daily lives. Black holes are not uniform. They exist across a vast spectrum of sizes, a hierarchy determined by mass. On the smaller end of this scale, we find the stellar mass black holes. The smallest one ever observed and confirmed by astronomers clocks in at around 3.8 solar masses. This unit, solar mass, is the standard currency of astronomical weight. One solar mass is equal to the entire mass of our Sunday, so even the smallest black hole contains nearly 4 times the material found in our own star, compressed into a city-sized sphere. On the absolute opposite end of the scale, we encounter the monsters, the supermassive black holes. These ancient giants have likely been in existence since the very dawn of the universe, growing alongside the galaxies they inhabit. These are objects weighing not just millions, but billions of solar masses. The physical size of these supermassive entities is difficult to conceptualize. If we look at the event horizon, the point of no return surrounding the black hole of one of these giants, its diameter would easily encompass our entire solar system. If you placed it where the sun is, the edge of the black hole would extend far beyond the orbits of Earth, Mars, Jupiter, and even Pluto. It is a region of darkness larger than the volume of space humanity has ever explored. But to understand what they are, we must understand where they come from. The black holes being created in the modern universe are the tombstones of titans. They are the final, inevitable stage in the life cycles of particularly massive stars. The life of a star is a constant, violent struggle from the moment a massive star is born, condensing out of a cloud of gas and dust. It is locked in a desperate balancing act between two opposing titanic forces. The first force is gravity. This is the inward force. The star's own immense mass creates a gravitational field that relentlessly pulls everything toward the center. Gravity wants to crush the star. It wants to pull every atom on the surface down into the core, compressing the star into the smallest possible volume. Without an opposing force, the star would collapse in seconds. The second force is the antagonist to gravity, nuclear fusion. Deep in the crushed depths of the star's core, the pressure and temperature are intense enough to force atoms to merge. In a young star, this process involves hydrogen atoms. Under normal circumstances, atomic nuclei repel each other. But here, they are crushed against other hydrogen atoms with such overwhelming force that they overcome that repulsion and combine. They fuse to form a heavier, denser element, helium. This is where the magic of physics occurs. If you were to weigh the two original hydrogen atoms and then weigh the resulting helium atom, you would find a discrepancy. The new helium atom is slightly lighter than the sum of its parts. A tiny fraction of mass has vanished during the fusion. That missing mass has not disappeared. It has been converted directly into energy, adhering to Einstein's famous equation. Because the speed of light is so large, even a tiny amount of converted mass releases a staggering amount of energy. This energy radiates outward from the center of the star as heat and light. This outward pressure acts as a pillar, holding up the outer layers of the star and counteracting the crushing force of gravity pushing in. In this state of hydrostatic equilibrium, the star is stable. It shines. It is a perfect engine. The star will remain in this relatively stable phase for millions or perhaps billions of years, depending on its mass. It continues as long as the reaction can be sustained, which is as long as it has hydrogen fuel to burn. However, fuel is finite. Time is the enemy. If the star is massive enough, far more massive than our sun, its death will not be quiet. Once the hydrogen in the core begins to run low, the outward pressure drops. Gravity momentarily wins, crushing the core tighter. This compression raises the temperature even higher, allowing the star to begin a new fusion cycle. It begins to combine the newly formed helium ash into even denser materials. Helium fuses into carbon. Carbon fuses into neon. Neon fuses into oxygen. Oxygen fuses into silicon. The star becomes layered like an onion, with different fusion reactions happening in concentric shells. The process accelerates. Burning hydrogen took millions of years. Burning helium takes perhaps 1,000,000. Burning carbon takes a few thousand. By the time the star is burning silicon, the fuel lasts only for days. Then, the star reaches the end of the line. It begins fusing iron. This is the fatal threshold. Iron is the most stable element in the universe. In all previous stages, hydrogen, helium, carbon, oxygen, the fusion process was exothermic, meaning it released more energy than it took to start the reaction. It created the outward pressure that fought gravity. Fusing iron is different. It is endothermic. To fuse iron into heavier elements does not release energy. It consumes energy. The moment iron is formed in the core, the engine dies. The iron ash builds up, creating a dead zone in the center of the star. It just sits in the core, growing larger and heavier, absorbing energy rather than creating it. Suddenly, the balance that held the star up for millions of years is gone. There is no energy pushing back against gravity. The support structure vanishes. Very quickly, in a fraction of a second, the scale tips completely. The collapse is immediate and catastrophic. The energy of this collapse is astounding. The outer layers of the star, which weigh billions of tons, suddenly have nothing holding them up. They fall inward. They are not just drifting. They are accelerating to speeds reaching 25% of the speed of light. Like a hammer striking an anvil, the mass of the star rushes down to meet the iron core. It slams into the center with such unimaginable force that the core cannot compress any further. The material bounces. The rebound of that blow creates a shockwave that travels outward, tearing the star apart. This is what we call a supernova. Matter and energy are blasted out across the universe from the crackback. It is one of the largest, brightest explosions possible in nature. The energy is so intense that in the few seconds of the explosion, the shockwave forces atoms together to create elements even heavier than iron. Gold, silver, lead, and uranium are all forged in this violent death throe. And what is left of the star after the outer layers are blown away? Well, it depends entirely on the mass of the core that remains. If the mass of the star, and thus the force of the inward blow, was high, but not too high, what remains is a neutron star. This is a small ball of matter, at most around 25 kilometers in diameter, roughly the size of a city like Manhattan or London. And yet, It is so densely packed with mass that it equals 1,000,000 Earths. The gravity has crushed the protons and electrons together to form neutrons. It is essentially one single, city-sized atomic nucleus. But if the original star was truly a giant, if the mass and thus the force of the collapse was big enough, even the neutrons cannot withstand the pressure. The neutrons themselves shatter. Physics, as we know it, breaks down. The material continues to collapse, smaller and smaller, denser and denser, until it occupies zero volume but retains all the mass. The gravity becomes so intense that not even light can escape its pull. We are left with a black hole. When you see a visual representation of a black hole, the perfectly black sphere you are looking at is not actually the black hole itself. It is the effect of the black hole. Scientists theorize that the black hole's true form, the source of all its gravity, is something far stranger. It is likely even smaller and denser than a neutron star. In fact, in the framework of general relativity, it is an object with all of its mass concentrated into a point that is infinitely small and infinitely dense. This theoretical point is called a singularity. It is a place where the laws of physics as we know them cease to function, but it is the origin point of the forces that warp time and space itself. However, we do not know this for certain, and the reason we do not know is because this singularity is hidden from us permanently by something called the event horizon. This horizon is the black sphere that we can see. All objects with mass exert gravity. We have understood this since the days of Newton. Gravity is what keeps our feet on the ground and the Earth in orbit around the Sunday. However, when Einstein came along in 1915 with his theory of general relativity, he redefined gravity. He showed that gravity is not a pulling force. Instead, gravity is the shape of space. A massive object, like the sun, creates a dent or a curve in the fabric of space. The Earth, in turn, thinks it is traveling in a straight line, but it is following the curve that the sun has created. A contemporary of Einstein, Carl Schwarzschild, took this new theory and reasoned from it a terrifying possibility. He calculated that if an object were massive enough and dense enough, it could create a dent in space that was infinitely deep. It could create enough gravity that the fabric of space itself would curve back in on itself. This would mean that light itself could not escape. Light is massless, but it must travel along the straight lines of space. If those lines are curved so extremely that they never lead back out, then the light becomes trapped. And if even the fastest thing in the universe, a massless photon, could not get out, then nothing else could. When you look at a picture of a black hole, you are not seeing the singularity itself. You are seeing the event horizon built around it. The event horizon is the precise demarcation line. It is the boundary where the curvature of space, or gravity, has become so powerful that the escape velocity equals the speed of light. Outside this line, light can still bend, but escape is possible. Inside this line, there is nothing but darkness, as all paths lead only inward. The effect of this massive object on space is one thing, but black holes also impact another fundamental aspect of the universe: time. You see, according to Einstein, space and time are not separate. They are a single, interwoven fabric called space-time. What affects space must also affect time. Mass warps space-time. This means that gravity affects the flow of time. This is not just a theory. It is a measured fact. Time on the surface of the Earth runs slightly slower than time for a satellite in orbit, where gravity is weaker. The singularity's near-infinite mass stretches space-time to such an extreme degree that the event horizon also marks the point where, from an outside perspective, time stops. This produces an interesting and counterintuitive phenomenon for an outside observer watching matter fall into a black hole. From your perspective, far away, you would see this matter a cloud of gas, a star accelerate toward the black hole. But as it gets closer and closer to the edge, it will appear to slow down. This is because the object is moving into a region of increasingly strong gravity, and its time is slowing down relative to yours. As it approaches the event horizon, it will slow down more and more until, just before the event horizon, it will seem to stop altogether, frozen in place. You will not ever see it cross the event horizon. There will be no satisfying absorption. Instead, the matter will gradually dim. The light waves it emits must fight their way out of the gravity well, and in doing so, they lose energy. They are redshifted, stretched out to longer and longer wavelengths, until they become invisible. The object will fade until you cannot see it anymore, its image permanently imprinted on the boundary of the black hole. When first theorized, astronomers and physicists were uncertain if black holes were actually mathematical curiosities or real objects. It was only 40 years later that the first solid evidence of a black hole was recorded. In 1964, using newly developed X-ray satellites, scientists noticed an object in the constellation Cygnus. It was invisible to normal telescopes, but it was emitting a large amount of X-rays. Strangely enough, scientists could not see the object itself. This surprised them. If it was a star, it ought to emit visible light, as well as X-ray radiation. This X-ray bright, visibly dark object was called Cygnus Zone. The mystery deepened. In 1970, as telescopes advanced, astronomers noticed that whatever Cygnus X Zone was, it had formed a binary orbit with a large, visible blue star in its system. The visible star was wobbling, being pulled by an unseen partner. This was the key. By observing the orbit of the visible star, scientists could calculate the mass of its invisible companion. They discovered that this invisible object was 15 times more massive than the Sunday. This was the smoking gun. The densest object then known to physics was a neutron star. But our understanding of physics dictated that a neutron star has an upper mass limit of about 3 times the mass of the Sunday. Any heavier, and its own gravity would overwhelm it. This object was 15 solar masses. It was too heavy to be a star, and too heavy to be a neutron star. Scientists realized that this was most likely the first ever discovered black hole. Since then, we have discovered many black holes. We now know that massive ones seem to exist at the center of most, if not all, galaxies. And we have even managed to take photographs of some. Dark blots or shadows silhouetted against a swirling, superheated ring of matter that surrounds them and falls into them. This ring is their accretion disk. This is how black holes can still be detected through X-rays. While the black holes cannot emit any electromagnetic radiation themselves, the X-rays that come from them actually originate from these accretion disks. This infalling matter, spiraling toward the event horizon, does not fall in a straight line. It forms a disk, and the inner parts of the disk orbit much faster than the outer parts. This extreme difference in speed, this shear, creates intense friction. This friction heats the matter to millions of degrees Celsius, far hotter than the surface of a star, causing it to glow brilliantly in X-rays just before it crosses the event horizon and vanishes forever. Black holes that have no infalling matter, no accretion disk, are basically invisible. They are quiet, dark, and can only be found if they warp the light of a star behind them, or, like Cygnus Own, if they are pulling on a visible companion. Exploring black holes is still a developing field in physics, and there is still much to learn. From what we have learned so far, you may wonder if a black hole could ever stop being a black hole, or if it will grow forever until there is no matter or radiation left in the universe. It would seem so. However, in 1974, in a paper titled Black Hole Explosions, physicist Stephen Hawking postulated that there was, in fact, a way that energy, and therefore mass, could leave a black hole. But to understand this, we must get into some extremely counterintuitive theory. We need to examine some core principles of quantum mechanics. To begin, we must first ask a difficult question. What is nothing? Imagine for a second a perfect patch of space with nothing inside it. There are no atoms of space dust. There is no radiation passing through it. As near as can be measured, nothing exists within it. And yet, is there really, truly nothing there? Something fundamental must exist here. We can tell that this is the case when a beam of light travels through it. If you are familiar with the properties of light, you will know that light is a wave of electrical and magnetic charge, constantly propagating with each other, moving forwards in a straight line. However, let us focus on that word, wave. A wave in the sea is the propagation of energy moving through the medium of water. If you were to look at an individual particle of water, it is not really traveling toward the shore. It is mostly just moving up and down, or in a small circle. And yet, because it passes energy to the atoms next to it, the energy travels towards the shore in a constant motion. Similarly, a sound wave moves by passing energy between air particles. Each particle only moves a tiny bit, becoming energized, and then passing that energy to the next particle in the line. The medium for a sea wave is water. The medium for a sound wave is air. But in our perfect vacuum of space, where there is nothing in it, where our photon of light is traveling in waves, have you ever stopped to wonder what exactly is waving? The medium is not water. It is not air. This hints at a fundamental something that must exist even in the most perfect vacuum. This is the fabric that makes up all of reality itself. Quantum physicists call this something a quantum field. Quantum fields are tough to wrap your head around, but they are the basis of modern physics. The universe is not made of particles. It is made of fields. There is an electron field, a photon field, a Higgs field. A particle, like an electron, is simply a localized vibration or an excitation in the electron field. Light is an excitation in the electromagnetic field. So, what is the vacuum? The vacuum is simply the lowest possible energy state of all these fields. It is the ground state, where there are no stable excitations, no particles. But lowest possible energy does not mean zero energy. According to the uncertainty principle of quantum mechanics, these fields are never perfectly still. Even in a perfect vacuum, the fields are constantly fluctuating. This quantum foam causes pairs of virtual particles, a particle and its antimatter twin, to spontaneously pop into existence, borrow energy from the vacuum for an impossibly brief moment, and then collide and annihilate each other, returning the energy. This seething, underlying reality of particles appearing and vanishing is the true nature of nothing. This fundamental quantum field is the fabric that Hawking's theory suggests is being affected at the edge of a black hole. There are events in the universe that offer a rare opportunity for observation. While a supernova in our immediate galactic neighborhood is not expected, there is an event anticipated that will allow for the observation of a different kind of stellar explosion. This is the recurring nova within the binary star system T Coronae Borealis, nicknamed the Blaze Star. This system is known for its periodic outbursts. Back in May of 1866, on a partly cloudy spring night in the west of Ireland, an amateur astronomer named John Birmingham was on his way home in the dark, just before midnight. His pace slowed occasionally so that he could look up at the stars. With a sharp eye, he scanned the night sky for familiar constellations, just as he had done countless times before. As his eyes reached the constellation known as the Northern Crown, he stopped, stunned. There was a new, bright star in this familiar pattern, a star that had not been there the night before. He had observed the recurring nova in the binary star T Coronae Borealis. This was an explosive astronomical event, one that helped to revolutionize our understanding of nova events and shape the field of stellar astronomy in the following decades. This was not a supernova, which is a one-time, star-destroying event. This was a recurring nova. This phenomenon requires a very specific setup. T Coronae Borealis is not one star, but two, locked in a close orbit. One of the stars is a red giant, an aging star that has swelled up, and its outer atmosphere of hydrogen is large and only weakly held by its own gravity. Its companion is a white dwarf. This is the incredibly dense, hot, Earth-sized core of a star that has already died. The two stars orbit so closely that the intense gravity of the dense white dwarf physically pulls or accretes material from the outer layers of the red giant. This stolen hydrogen gas streams from the red giant and forms a layer, like an ocean, on the surface of the white dwarf. Over time, this layer of hydrogen builds up. As more and more material rains down, the pressure and temperature at the bottom of this layer increase. It becomes compressed to an extreme degree. Eventually, it reaches a critical point, a specific temperature and density that ignites a runaway thermonuclear fusion reaction. The entire layer of stolen hydrogen ignites at once, fusing into helium in a catastrophic explosion. This is the nova. It is this sudden, brilliant flash of light that John Birmingham saw. Crucially, this explosion only ejects the accreted layer of fuel. The white dwarf and the red giant themselves are not destroyed. Once the fuel is gone, the explosion subsides. But the process of accretion begins again. The white dwarf, now clean, immediately starts pulling more hydrogen from its red giant companion, and the system begins to reload for the next explosion. This is why the event is recurring. The cycle in this system is estimated to be about 80 years, and for those of us alive today, we will have the unique opportunity to experience the same recurring nova explosion that captured Birmingham's fascination more than 150 years ago on that cool spring night in Ireland. And you will not even need a telescope or any fancy equipment to see it. Why is it going to happen again? And when will it happen? The nickname Blaze Star serves as a convenient shorthand for astronomers, but it is physically misleading. When we look at this point of light, known scientifically as T Coronae Borealis, we are not looking at a single star. We are looking at a binary system. This entails two individual stars locked in a gravitational embrace, orbiting a common center of mass. It is the volatile parasitic relationship between these two specific stars that drives the mechanism for the recurring nova explosion we witness roughly every 80 years. To understand the rarity of this, we must first understand the norm. It is estimated that perhaps 50% of all the stars we see in the night sky are not solitary wanderers like our sun, but are part of multiple star systems. However, mere proximity is not enough to create a blaze star. It requires a specific evolutionary mismatch. Both of the stars in this binary system began their lives as average-sized stars, roughly similar in mass and composition to our own Sunday. However, stars do not age at the same rate. Their lifespan is dictated by their mass. In this system, each star is currently at a drastically different stage in its life cycle. To comprehend these stages, let us look at the trajectory of our own star. Our sun is currently 4.6 billion years old. In the terminology of stellar evolution, it is a middle-aged main sequence star. It is stable, but this stability is finite. In approximately 5 billion years, the sun will exhaust the hydrogen fuel in its core. When this happens, the delicate balance between gravity pulling in and radiation pushing out will be broken. The core will collapse, but the outer layers, driven by fusion moving into shells around the core, will expand drastically. The sun will enter its red giant phase. It will swell to a size so enormous that its physical surface will likely engulf the orbits of Mercury, Venus, and possibly even Earth. As the red giant consumes its remaining fuel over the subsequent period, somewhere between 5 to 10 billion years from now, it will become unstable. Eventually, it will gently cast off its vast, tenuous outer layers into space. This ejected material will form a glowing shell known as a planetary nebula. Left behind at the center of this nebula will be the exposed core of the dead star. This remnant is a white dwarf. A white dwarf is an object of extreme physics. It is an object roughly the size of planet Earth, yet it contains a significant fraction of the mass of the original star. It is incredibly dense. A single teaspoon of white dwarf material would weigh as much as an elephant on Earth. These are often referred to as dead stars because fusion has ceased. They have no internal engine. They will simply spend the next 10 trillion years slowly radiating their stored heat into the cold vacuum, cooling until they eventually fade into darkness. This is the context for our blaze star system. Both stars in the T Coronae Borealis system were once like the Sunday, but today they are the ghosts of our sun's future. One has already evolved into a bloated red giant. The other has died and become a dense white dwarf. They are further along in their stellar evolution than our sun, and they are orbiting close enough to interact. In fact, this interaction is the precise engine for the recurring nova we are expecting to witness in the year 2024. It all comes down to gravity and proximity. As the red giant component of the system heats up and its outer shell expands, it reaches a point where its own gravity can no longer hold onto its outer layers against the pull of its companion. The material, primarily hydrogen gas, is continually stripped away by the immense, concentrated gravitational pull of the neighboring white dwarf. This process creates a bridge of matter between the two stars. The white dwarf acts like a cosmic siphon. However, the gas does not fall directly onto the surface. Due to the orbital motion, it spirals in, forming a flat, rotating disk known as an accretion disk. Friction within this disk heats the gas as it slowly loses angular momentum and rains down onto the surface of the white dwarf. Over the course of 80 years, the white dwarf collects this stolen material. It accumulates a new atmosphere of hydrogen, a layer that gets thicker and heavier with each passing day. Gravity compresses this layer. The pressure and heat at the bottom of this hydrogen ocean builds steadily. It is a pressure vessel, and the tension is rising. Eventually, the temperature at the base of the hydrogen layer reaches a critical threshold, millions of degrees. At this precise moment, the conditions mimic the core of a living star. A thermonuclear reaction is triggered, but unlike in a stable star, where the reaction is contained, here the entire layer ignites at once. The buildup becomes too much. The result is a runaway fusion explosion that blasts away all of that built-up material in a flash of energy. This is the mechanism of the nova. The pressure and heat that have accumulated on the white dwarf for 8 decades are released in seconds. The result is an explosion so powerful that it can make the star appear 1,500 times brighter than usual. From our vantage point on Earth, 3,000 light years away, a star that is normally invisible to the naked eye suddenly flares into brilliance. It is important to make a clear scientific distinction here. How is this nova different from the more famous supernova? The names are similar, but the mechanisms and outcomes are radically different. The event on the Blaze star is technically referred to as a classical nova. While the explosion is massive by human standards, it is, in stellar terms, a surface phenomenon. It is a skin eruption. The explosion blasts away the accumulated layer of stolen hydrogen, but, and this is the key, it does not destroy the white dwarf itself. The underlying star remains intact. This survival is what allows the process to be cyclical. Once the explosion clears, the white dwarf is still there, its gravity is still strong, and the red giant is still nearby. The siphoning begins again immediately. The tank starts to refill, and the countdown to the next explosion, 80 years later, restarts. On the other hand, a supernova is a terminal event. For a solitary star to destroy itself at the end of its life in a grandiose supernova, it must meet specific criteria. It usually must start its life with more than 8 times the mass of our Sunday. These stars are far more massive than the components of the Blaze star system. When such a massive star collapses, it is not just blowing off a surface layer. The core itself collapses. The resulting explosion is millions of times brighter than the Blaze nova. It obliterates the star, leaving behind only a neutron star or a black hole. The closest candidate we have for such an event in the near future is the red supergiant, Betelgeuse. This is a star that often appears as one of the 10 brightest in our night sky, despite being located approximately 640 light years away. When scientists speak of the near future regarding Betelgeuse, it is essential to calibrate our expectations to the cosmic perspective. Researchers do not expect this star to go supernova for perhaps tens of thousands of years. In the lifespan of the universe, that is the blink of an eye. In human terms, it is an eternity. But, purely as a thought experiment, imagine the awe-inspiring view that humanity would witness if Betelgeuse were to explode tomorrow. The energy release would be staggering. After the initial explosion, the star would condense into a point of light as bright as a full moon. It would be so luminous that it would cast shadows at night and remain clearly visible in the blue sky during the day for weeks. What a sight that would be. However, while extraordinarily rare, a Betelgeuse event would not be the first time humanity has witnessed a supernova. And the Blaze star is certainly not the only nova or supernova in history to be visible to the naked eye. We have records. The oldest confirmed record of a supernova dates back nearly 2 millennia. It is now cataloged as SN 185. In the year 185 AD, Chinese astronomers recorded the appearance of a guest star. They noted that this strange new light remained visible in the night sky for a staggering 8 months before fading away. For centuries, this was just a story in ancient texts, but modern X-ray and radio astronomy have allowed us to look at the exact region of the sky described in those texts. There, astronomers found a remnant called RCW86, a shell of gas expanding from a central point. By calculating the speed of the expansion and winding the clock backward, they confirmed that the explosion occurred almost exactly in the year 185. The ancient observation was accurate. There have only been a handful of supernovae visible to the naked eye in recorded history. One of the most famous and scientifically significant instances occurred in the year 1604. This event was documented meticulously by the German astronomer Johannes Kepler. This was a pivotal moment in the history of science. At the time, the prevailing Aristotelian view was that the heavens were perfect and unchanging. A new star appearing challenged this dogma fundamentally. Kepler's supernova was so bright that people could see it clearly during the daytime for over 3 weeks. Kepler tracked its brightness and position with such precision that his data is still used by astronomers today to understand the expanding cloud of debris that remains. So, as we wait for the Blaze star to erupt in our own time, we are participating in a very long tradition of humans looking up, noticing that the unchanging sky has changed, and wondering why. What we are preparing to observe in the remaining months of 2024 is expected to be one of the brightest classical novae of this entire century. And just like a supernova, this is a rare and noteworthy occurrence. But the distinction regarding its rarity requires context. In the vastness of the observable universe, classical novae are actually quite common. Somewhere in the billions of galaxies that surround us, these explosions are happening constantly. Even within our own Milky Way galaxy, classical novae that are technically visible to the naked eye occur relatively frequently statistically, about once every year or two. However, there is a significant difference between technically visible and easily observable. Most of these events occur at such vast distances or are obscured by so much interstellar dust that while they might breach the threshold of naked eye visibility, they are barely perceptible. They appear as faint, ghostly smudges that only an experienced observer looking at exactly the right coordinates in a perfectly dark sky would ever notice. They are rarely bright enough for the untrained or unaided eye to spot from a city or a suburb. The Blaze star event, on the other hand, is an entirely different category of spectacle. It is expected to be one of the brightest classical novae to appear in our night sky in nearly 50 years. To understand exactly how bright that is and why this matters, we must delve into the specific system astronomers use to quantify the brilliance of celestial objects, the scale of apparent magnitude. This system can be counterintuitive to the modern mind because it is ancient. It is based on a classification system developed by the Greek astronomer Hipparchus over 2,000 years ago. He simply divided the stars he could see into 6 categories. The brightest stars he called first magnitude, and the faintest stars he could barely see he called sixth magnitude. Because of this history, the scale works backward compared to most modern measurements. The smaller the number, the brighter the object. A star with a magnitude of 1 is brighter than a star with a magnitude of 2. a star with a magnitude of 2 is brighter than a star with a magnitude of 3, and so on. It is also not a linear scale. It is logarithmic. A difference of 1 point in magnitude corresponds to a difference in brightness of about 2.5 times. This means a magnitude 1 star is not just slightly brighter than a magnitude 6 star, it is exactly 100 times brighter. To place the blaze star in context, let us look at some familiar anchors in our sky. Typically, under perfect conditions on the darkest night, far away from city lights, the limit of human vision is about magnitude 6.5. Anything dimmer than this number, or higher, on the scale, is invisible to us without binoculars or a telescope. The 7 bright stars that form the famous Big Dipper asterism in the constellation Ursa Major serve as a good reference. They range from the dimmest at magnitude 4.8 to the brightest at magnitude 1.7. Moving up the scale of brightness, we encounter Polaris, the North Star. Despite its fame, it is not blindingly bright. It shines at a steady magnitude of 1.97. The brightest star in the entire night sky is Sirius, the Dog Star. It is so bright that it dips into the negative numbers, shining at a magnitude of negative 1.44. The planets can be even brighter. Venus, at its peak, can reach magnitude negative 4.4. The full moon shines at magnitude negative 12.7. And the sun, the overwhelming source of light in our system, clocks in at a staggering negative 26.7. So, where does the blaze star fit into this hierarchy? Normally, in its quiet phase, the magnitude of T Coronae Borealis is roughly 10. This places it far, far below the threshold of human vision. It is invisible, requiring a telescope to be seen. It is just another dark point in the void. But during the nova explosion, which happens once every 80 years, the physics of the system change violently. The thermonuclear detonation on the white dwarf's surface causes its light output to surge. The star peaks at a magnitude between 3 and 2. This means it leaps from the darkness to rival the brightness of Polaris, the North Star. It transforms from an invisible object into one of the top 50 brightest stars in the sky. It appears, seemingly from nowhere, to take a prominent place in the heavens. This sudden appearance connects us to the etymology of the word itself. Nova comes from the Latin word nova, meaning new. Today, we understand the nuclear physics behind the event, but it is worth pausing to consider the psychological impact this sight had on our ancestors. In the ancient Aristotelian view of the cosmos, the stars were considered fixed and immutable. The heavens were a realm of perfection that did not change. For an ancient astronomer, seeing a nova stella, a new star appear where none had existed before, was not just a curiosity, it was a shock. It was a violation of the rules of the universe. It proved that the heavens were dynamic, changeable, and perhaps violent. We have seen similar events in recent history. In 2013, Nova Centauri surprised astronomers. It occurred in the southern constellation of Centaurus and became one of the brightest novae in over a century, reaching a peak magnitude of 3.3. However, the blaze star has a history of outperforming expectations. The last time this specific system exploded was in 1946. During that event, it reached a magnitude of 3. But predictions for this year's event suggest it could be even more intense. Current models indicate it creates a fireball that could reach a peak magnitude of 2.0. If these models hold true, for a brief window of time, looking at the blaze star will be exactly like looking at the North Star. But this stellar show will not last long. The nature of a nova is transient. The explosion burns through the accumulated hydrogen fuel rapidly. As the shell of ejected gas expands outward into space, it cools down. As it cools, it becomes transparent, and the light fades. The blazed star may only be visible to the naked eye for a few days, perhaps a week at most, before it dims back down below the threshold of magnitude 6, fading back into the darkness to begin its 80-year slumber once again. There is no exact calendar date for when this will happen. The star operates on its own internal physics, not our schedule. However, based on the dip in brightness that precedes the eruption, scientists predict it is imminent, likely occurring in the second half of 2024. So, how do you prepare to witness this? You need to know where to look before the light arrives. To find the blazed star in the night sky, you do not need expensive equipment. You need to learn to star hop. You will be looking for a specific region of the sky between two large constellations, Boötes and Hercules. First, locate the very bright star, Arcturus. You can find it by following the curve of the Big Dipper's handle. Remember the phrase arc to Arcturus. Once you have found this bright orange star, look nearby for a distinct, small semicircle of stars. It looks like a small celestial bowl or a tiara. This is the constellation Corona Borealis, the Northern Crown. It is a C-shape of stars located roughly between the kite shape of Boötes and the keystone shape of Hercules. The Northern Crown is small but distinct. If you trace the curve of the crown, starting from the side closest to Boötes and moving toward Hercules, you are looking for the region just off the edge of the crown. When the nova occurs, the blazed star will appear as a new jewel in this crown, appearing just below the corner star of the semicircle. If you familiarize yourself with this pattern now, while the sky is dark, the sudden appearance of the intruder star will be immediately obvious to you when the event occurs. If you have access to a powerful amateur telescope or can visit a local observatory, you may even be able to spot the binary star now, before the nova begins. Seeing it in its quiet state will allow you to truly compare the before and after, giving you a visceral sense of the power involved in the explosion. These novae serve as a powerful reminder. They remind us that the stars, which can seem eternal and unchanging from the perspective of a human lifespan, actually possess astonishing life cycles. They are dynamic engines that undergo drastic changes and dramatic explosions. This is a cosmic fireworks show, but it is also a laboratory. Each nova provides a unique opportunity for astronomers to gather critical data. By analyzing the light from the blazed star spectroscopy that reveals the chemical composition of the ejected shell and X-ray timing that reveals the speed of the explosion, we refine our understanding of stellar evolution. This data helps us understand how binary star systems function, how matter behaves under extreme density, and how elements are distributed throughout the galaxy. This upcoming nova will be one of the most accessible and exciting astronomical events we will get to see in our lifetime. It is a connection to the past observations of 1946 and 1866, and a gift to the future of science. So, keep an eye on the news, and more importantly, keep an eye on the night sky. Familiarize yourself with the Northern Crown. And when that new light appears, take a moment to feel just a little bit luckier to be alive, standing on this rock, able to look up and experience the violent beauty of the universe. While the recurring nova of T Coronae Borealis is a spectacular display of stellar physics, within the grand hierarchy of cosmic violence, it is merely a spark, if we wish to understand the true power of the universe, and more importantly, if we wish to understand the origins of the very atoms that make up the world around us, we must look beyond the nova. We must look to the most luminous electromagnetic events known to occur in the universe, gamma-ray bursts. The discovery of these cataclysmic events is one of the great accidental stories of science. It began not in an observatory, but in the tense, paranoid atmosphere of the Cold War. In the 1960s, the United States launched a series of satellites known as the Vela constellation. Their mission was strictly military. They were equipped with X-ray, gamma-ray, and neutron detectors designed for one specific purpose: to monitor the Earth and verify that the Soviet Union was abiding by the Nuclear Test Ban Treaty. The satellites were watching for the distinct flash of illegal nuclear weapons testing in the atmosphere or on the far side of the moon. On July 2nd, 1967, the Vela satellites detected a flash. It was a pulse of gamma radiation, the most energetic form of light in the universe. But there was a problem. The data showed that the signal did not come from the Soviet Union. It did not come from Earth at all. It came from deep space. Over the next few years, these satellites detected more and more of these bursts. They were random, appearing from all different directions in the sky, and they were terrifyingly powerful. To put the scale of energy into perspective, in a few brief seconds, a typical gamma-ray burst, or GRB, can release more energy than our sun will emit in its entire 10 billion year lifetime. If a GRB were to occur within our own galaxy, directed straight at us, it could strip away our ozone layer and cause a mass extinction event. Fortunately, most of these events occur in distant galaxies, billions of light years away. For decades, the source of these bursts was a mystery. Today, we have identified two primary engines for these events, and understanding them requires us to revisit the stellar graveyards we discussed earlier. The first type are long-duration bursts, lasting more than 2 seconds. These are the death screams of massive stars, far larger even than Betelgeuse. When these hypergiants collapse, they do not just form a simple black hole. The core collapse is so violent that it drives jets of particles outward at speeds approaching the speed of light. As these jets punch through the dying star, they emit a focused beam of gamma rays. We only see the burst if we happen to be looking directly down the barrel of the gun. But it is the second type, the short-duration bursts, lasting less than 2 seconds, that holds the answer to a fundamental question about our own existence. These bursts are caused by the collision of two neutron stars. Recall that a neutron star is the ultra-dense, city-sized core left over from a supernova. Sometimes, two massive stars are born together, live together, and die together, leaving behind two neutron stars locked in a decaying orbit. Over billions of years, they spiral closer and closer, losing energy in the form of gravitational waves, ripples in the fabric of space-time itself. Eventually, they touch. The resulting event is called a kilonova. This is not just a larger explosion. It is a different kind of explosion. It is a cosmic forge. And this brings us to a chemical mystery that plagued astronomers for most of the 20th century. We know where the elements come from. We know that the Big Bang created hydrogen and helium. We know, as we discussed with Betelgeuse, that stars fuse these lighter elements into heavier ones: carbon, nitrogen, oxygen, silicon. But we also established a hard limit: the iron wall. Ordinary stars cannot fuse elements heavier than iron because doing so consumes energy rather than creating it. So, If stars stop at iron, look at the world around you. Look at the gold in a wedding ring. Look at the lead in a battery. Look at the iodine in your medicine cabinet, or the uranium in a nuclear reactor. These are all heavy elements, far heavier than iron. If stars cannot make them, and the Big Bang did not make them, where did they come from? For a long time, the standard answer was supernovae. The theory was that during the explosion of a massive star, there was enough excess energy to force atoms to fuse into these heavier states. And while this is true to an extent, modern calculations showed that standard supernovae simply do not produce enough neutrons to create the vast amounts of gold and platinum we see in the universe. The math did not add up. There was a missing source. The answer lies in the violence of the kilonova and a process known to physicists as the R process, or rapid neutron capture. To build a heavy element like gold, you need to take a lighter nucleus and force-feed it neutrons. If you add neutrons slowly, one by one, the nucleus has time to decay radioactively back into a stable, lighter state before it can grow heavy. This is the S process, or slow process, that happens in dying red giants, and it can make elements like lead, but it is too slow to make the really heavy, exotic metals. To make gold or uranium, you need speed. You need to bombard the seed nucleus with so many neutrons, so quickly that it has no time to decay. You have to force it to bulk up, swelling its mass massively in a fraction of a second before it stabilizes. You need a distinct environment where neutrons are not just available, but are overwhelming. You need a storm of neutrons. There is only one place in the universe where such a storm exists: the collision of two neutron stars. When these ultra-dense objects smash into each other, they shatter. An enormous amount of neutron-rich matter is sprayed out into space. In this hot, expanding cloud of debris, the R process runs wild. Atoms are bombarded by neutrons, transforming from iron to gold, to platinum, to plutonium in the blink of an eye. For decades, this was just a theory. But on August 17th, 2017, humanity witnessed the proof. Detectors on Earth, LIGO in the United States, and Virgo in Italy picked up a signal. It was not light. It was a gravitational wave. A ripple in space-time passed through the Earth, caused by the merger of two neutron stars, 130 million light-years away. Almost simultaneously, space telescopes detected a short gamma-ray burst from the same location, and then optical telescopes on the ground saw the afterglow. By analyzing the light from that explosion, this specific kilonova event, cataloged as GW1708, 17 astronomers found the spectral fingerprints of heavy elements. They saw the signature of strontium, platinum, and gold. The calculations were staggering. In that single collision, the universe forged a mass of pure solid gold that is estimated to be 10 to 20 times the mass of the entire Earth. Think about that for a moment. A single event created more gold than has ever been mined in human history, more than exists in our entire planet's crust. Multiplied by 20, it was blasted out into the galaxy as a cloud of dust, mixing with other gas clouds, eventually coalescing into new solar systems. This realization changes how we view our own solar system and our own bodies. We have often heard the poetic sentiment that we are made of stardust. This is scientifically accurate, but we can now be much more specific about which stars we are made of. This is the concept of cosmic alchemy. The atoms in your body have different lineages different histories that trace back to different violent ancestors. Consider the hydrogen in the water molecules that make up 60% of your body. That hydrogen is ancient. It was formed in the Big Bang 13.8 billion years ago. It has not changed since the dawn of time. You are carrying pieces of the cosmic beginning within you. Now, look at the blood in your veins. The hemoglobin molecule, which transports oxygen, relies on a central atom of iron. That iron was forged in the crushing core of a massive star, perhaps a star like Betelgeuse, just before it collapsed and died in a supernova explosion billions of years ago. The explosion scattered that iron into the cloud that became our sun and Earth. Your blood is red because of the death of a giant. Consider the calcium in your bones and the teeth in your jaw. These elements were likely cooked up in the slow death of smaller stars, or white dwarf supernovae, similar to the mechanism we discussed with the blaze star, where white dwarfs explode entirely. And if you wear a ring of gold, or a necklace of silver, or use a smartphone containing rare earth elements, you are touching the remnants of a kilonova. Those atoms were forged in the violent, cataclysmic collision of two neutron stars. They traveled across the void of space, survived the formation of the Earth, were mined from the ground, and ended up in your hand. We are not just observers of the universe. We are composed of its history. We are the museum of its most violent events. This perspective brings a new layer of appreciation to the night sky. When we look up at the northern crown to find the blaze star, or when we look at Orion to see Betelgeuse, we are not just looking at distant lights. We are looking at the processes that made us possible. But the universe is not just creating matter. It is also organizing it in ways that defy our intuition. As we move from the scale of atoms to the scale of galaxies, we encounter structures that are terrifying in their magnitude. We have spoken about black holes as individual objects, singularities that warp space. But black holes do not just sit alone in the dark. They have a profound influence on the galaxies they inhabit. In fact, there is a deep, unexplained connection between the size of a galaxy and the size of the supermassive black hole at its center. This brings us to one of the most awe-inspiring structures in the universe, the quasar. A quasar is technically a type of active galactic nucleus, but that dry scientific term hides the reality of what it is. A quasar is a supermassive black hole weighing billions of solar masses that is feeding continuously. Unlike the black holes we observe in our own galaxy, which are relatively quiet, a quasar is consuming matter at a rate that is difficult to comprehend. It can devour the equivalent of hundreds of Earths every minute. As this material spirals in, the friction we discussed earlier reaches levels that are catastrophic. The accretion disk of a quasar glows so brightly that it can outshine the entire galaxy of billions of stars that surrounds it. Some quasars are so luminous that they are visible from the very edge of the observable universe. The light from these objects has traveled for 12 or 13 billion years to reach us. We are seeing them as they were when the universe was in its infancy. But quasars are not just bright, they are engines of destruction and creation. As the black hole feeds, it does not swallow everything. Magnetic fields channel some of the infalling material into jets similar to the gamma-ray bursts, but on a galactic scale. These jets blast out from the poles of the black hole, traveling for hundreds of thousands of light years. These jets heat up the gas in the entire galaxy. By heating the gas, they prevent it from cooling down and collapsing to form new stars. In this way, A single supermassive black hole, an object that is physically tiny compared to the galaxy, controls the fate of the entire system. It can kill a galaxy, stopping star formation forever, turning a vibrant spiral galaxy into a dead, red elliptical galaxy. This feedback loop suggests that the universe is a balanced ecosystem. The violence of the black hole regulates the growth of the galaxy. Without this violence, the universe as we know it, with its structured galaxies and star systems, might not exist. We see this balance closer to home as well. Our own Milky Way galaxy has a supermassive black hole at its center, known as Sagittarius A star. It is currently quiet, a sleeping giant. But evidence suggests that it was not always this way. Astronomers have discovered vast bubbles of gamma-ray emitting gas extending above and below the plane of our galaxy, the Fermi bubbles. These are likely the scars of a past meal, remnants of a time millions of years ago when our own central black hole was active, blasting out energy and shaping the galaxy we live in today. From the iron in our blood to the shape of the Milky Way, we are defined by these processes. As we continue our exploration, we must also address the environment in which all of this happens. We often think of space as empty, and we discussed earlier the quantum fields that permeate the vacuum. But on the largest scales, space is filled with something else, something we cannot see, touch, or interact with directly, yet which makes up the majority of the mass in the universe: dark matter. When astronomers look at a spiral galaxy, like the pinwheel galaxy we viewed in the Hubble images, they notice something strange about the way it spins. According to the laws of gravity derived by Newton and Einstein, stars on the outer edge of a galaxy should move slower than stars near the center. It is the same reason Pluto moves slower than Mercury. But when we measure the speeds of stars in galaxies, we find that this is not true. The stars on the edge are moving just as fast as the stars in the middle. They are moving so fast that, by all rights, they should be flung out into deep space. The visible mass of the galaxy, the stars, gas, and dust is not enough to hold them in. The gravity is too weak. The galaxy should fly apart, but it does not. This implies that there is something else there. A vast, invisible halo of matter surrounds every galaxy, providing the extra gravity needed to hold it together. We call it dark matter not because it is shadowy, but because it does not interact with light at all. It does not reflect, emit, or absorb light. We only know it is there because of its gravitational effect on the things we can see. Calculations suggest that for every 1 kilogram of normal matter, stars, planets, you, me, there are 5 kilograms of this invisible dark matter. It is the scaffolding of the cosmos, the visible universe. Everything we have discussed so far, from Betelgeuse to the Blaze Star, from neutron stars to gold atoms, is just the icing on a cake made of dark matter. And it gets stranger. While dark matter pulls things together, there is another force pushing things apart. In the late 1990s, astronomers trying to measure the expansion of the universe using supernovae specifically, using them as standard candles to measure distance, found something shocking. Everyone expected the expansion of the universe to be slowing down, gravity slowly pulling the brakes on the Big Bang. But the data showed the opposite. The expansion is speeding up. The galaxies are flying away from each other faster and faster every day. There is a mysterious energy pressure inherent to the vacuum of space itself that is pushing the universe apart. We call this dark energy, and it makes up roughly 68% of the total energy budget of the universe. So, when we look at the night sky, we must be humble. Everything we can see, every star, every galaxy, every atom, comprises only about 5% of the universe. The other 95% is composed of dark matter and dark energy, two profound mysteries that we have named but do not yet understand. We are living in a golden age of astronomy, where our instruments are finally sensitive enough to detect the ripples of space-time from a kilonova, and our theories are robust enough to explain the origin of the gold in our rings. But we are also standing on the precipice of the unknown, staring into the 95% of reality that is still hidden from us. This journey, from the humble observation of a new star in the northern crown to the realization of the invisible forces shaping the cosmos, serves as a testament to human curiosity. We are small, momentary creatures, living on a rock orbiting an average star, but through observation and reason, we have managed to reconstruct the biography of the universe itself. Since we have acknowledged that dark energy is accelerating the expansion of the universe, we must follow that logic to its ultimate, inevitable conclusion. If this expansion continues unchecked, as all current data suggests it will, it paints a picture of the far future that is both majestic in its scale and terrifying in its silence. Astronomers and cosmologists call this scenario the Big Freeze, or the heat death of the universe. To understand this, we must look far beyond the timelines we are used to. We are not talking about billions of years anymore. We are talking about eras. As space expands, the galaxies outside of our own gravitationally bound cluster, the local group will be pushed away from us faster than the speed of light. This does not violate physics. Space itself can expand faster than light, carrying the galaxies with it. Eventually, they will cross a cosmic horizon and disappear from our view forever. If there are civilizations alive trillions of years from now, born on a planet orbiting a long-lived red dwarf star, their astronomers might look up and see only their own galaxy, floating in an infinite, featureless, and completely black void. They would have no way of knowing that other galaxies ever existed. They would have no evidence of the Big Bang, as the cosmic background radiation would have been stretched into undetectability. The evidence of the universe's rich history is slowly being erased by the expansion of space itself. Inside the isolated galaxies, the supply of gas needed to form new stars is finite. The great star-forming nurseries we observed earlier, the pillars of creation in the Eagle Nebula, the chaotic beauty of the Orion Nebula, will eventually dissipate. The gas will be consumed or flung out into the intergalactic void. The era of star birth, the era we are lucky enough to live in, will end. One by one, the existing stars will burn through their fuel and die. The massive ones will explode in supernovae, briefly illuminating the dark before fading. The smaller stars, like our sun, will shed their layers and shrink into white dwarfs. The smallest stars, the red dwarfs, will burn slowly for trillions of years, but eventually, even they will run out of hydrogen. The lights will go out. The universe will transition from the stelliferous era, the age of stars, into the degenerate era. In this cold future, the cosmos will be inhabited only by the corpses of stars, brown dwarfs, white dwarfs, neutron stars, and black holes. Occasionally, two dead stars might collide, creating a brief flash of light in the darkness, but these will be rare flickers in an endless night. Eventually, theory suggests that even the white dwarfs will cool down completely, ceasing to emit any heat, becoming black dwarfs, cold, dark spheres of crystallized carbon floating in the void. In this dark future, black holes will become the dominant rulers of the cosmos. They will sweep up the remaining debris, growing larger and larger, dominating the gravitational landscape. But the laws of thermodynamics differ for no one. Even the black holes are not eternal. This brings us back to the concept of Hawking radiation that we touched upon earlier. Quantum mechanics dictates that the vacuum of space is not empty, but filled with virtual particle pairs popping in and out of existence. When this happens on the very edge of a black hole's event horizon, one particle falls in and the other escapes. To an outside observer, this looks like the black hole is emitting radiation. This process consumes the mass of the black hole. Currently, the background temperature of the universe is warmer than most black holes, so they are absorbing more energy than they lose. They are still growing, but in the deep future, as the universe expands and cools to a temperature indistinguishable from absolute zero, that balance will flip. Over time scales that are impossible for the human mind to truly comprehend, numbers with so many zeros that writing them out would fill a library, the black holes will slowly evaporate. They will bleed their mass away into the void as weak radiation. When the last supermassive black hole evaporates in a final, faint flash of gamma rays, the universe will consist of nothing but a thin, uniform soup of photons and subatomic particles separated by unimaginable distances. Entropy will have reached its maximum. The universe will be in a state of perfect equilibrium. No energy can flow because everything is the same temperature. No work can be done. No life can exist. Time, in any meaningful sense, will cease to have definition because nothing changes. This sounds bleak. It is a story of ultimate finality. But there is a profound beauty and an urgent lesson in realizing this. It forces us to appreciate the now. We are living in the prime of the universe. We exist in that brief, golden window of time where the universe is vibrant, active, and chaotic enough to support complexity and life. We are the universe's way of witnessing its own glory before the lights go out. The fact that we are here with eyes to see and minds to wonder is statistically improbable and incredibly precious. And we are not just witnessing it with our biological eyes. We are building machines to see what our eyes cannot, to peer deeper into this golden age and understand our place within it. If the Hubble Space Telescope was the machine that opened our eyes to the visual beauty of the cosmos, its successor, the James Webb Space Telescope, is the machine that allows us to see through the veil of time and dust. To understand why this specific tool is so revolutionary, we must understand the engineering of light. We discussed how the expansion of the universe stretches light waves. As light travels through the expanding fabric of space for billions of years, it gets pulled like a piece of taffy. Visible light is stretched until it becomes infrared light. This is why the James Webb Telescope is designed to see primarily in the infrared spectrum. It is, quite literally, a time machine. By looking at infrared light, it can see the very first galaxies that formed just a few 100 million years after the Big Bang. These are objects whose light has been redshifted so severely that they are completely invisible to Hubble and the human eye. But infrared offers another critical advantage, one that brings us back to the star-forming regions we explored earlier, like the Eagle Nebula. Visible light has a short wavelength, which means it easily crashes into small particles like dust grains. When we looked at the pillars of creation, we saw vast, majestic walls of dust. They were beautiful, but they were opaque. We could not see what was happening inside them. Infrared light is different. It has a longer wavelength, which allows it to slip past the dust grains without bouncing off, much like radio waves can pass through the walls of your house. For the first time, we can look inside the cocoons. We can see the protostars that are currently forming, hidden deep within the dark pillars. We can see the messy, violent process of star creation as it happens. We can see the disks of dust and gas swirling around these newborns, the raw materials for future planets. And what we are finding around these new stars brings us to the most compelling and ancient question of our species. Are we alone? For most of human history, the existence of planets around other stars was a philosophical guess. It was a statistical assumption, but we had no proof. Today, it is a confirmed fact. We now know that planets are as common as stars. On average, every star you see in the night sky has at least one planet orbiting it. The search for these exoplanets has shifted from simply finding them to analyzing them. We are no longer just counting them. We are tasting their air. The method we use is a triumph of precision. It is called transmission spectroscopy. We stare at a distant star and wait for a tiny, periodic dip in its brightness. This dip is caused by a planet passing in front of the star, blocking a fraction of its light. This is known as a transit. But we can do more than just measure the size of the planet by the shadow it casts. As the planet passes in front of the star, a tiny, infinitesimal sliver of starlight passes through the planet's atmosphere on its way to Earth. Think about a sunset on Earth. The sunlight passes through a thick layer of our atmosphere. The air molecules scatter the blue light, letting the red light pass through. The atmosphere acts as a filter. The same thing happens on alien worlds. The gases in that distant atmosphere absorb specific wavelengths of light. By capturing that light and spreading it into a spectrum, a rainbow, we can look for the missing colors. These missing slices serve as a barcode, a chemical fingerprint of the atmosphere. If the planet has water vapor, it will block a specific frequency of infrared light. If it has methane, it will block another. If it has carbon dioxide, it will block yet another. We have already found water vapor, carbon dioxide, sodium, and methane in the skies of alien worlds hundreds of light years away. We have detected clouds made of vaporized rock on hot Jupiters and skies that rain molten iron. But the Holy Grail is to find this on a rocky, Earth-sized world. Consider the TRAPPIST-1 system, a red dwarf star located 40 light years away. This system is a marvel. We have discovered 7 Earth-sized planets orbiting this single star. They are packed so close together that if you stood on the surface of one, the other planets would appear in the sky as large as our moon, showing visible phases and surface features. 3 of these planets orbit within the Goldilocks zone, or the habitable zone. This is the narrow band of distance from the star, where temperatures are just right, not too hot, not too cold for liquid water to exist on the surface. The James Webb Space Telescope is currently turning its massive golden mirror toward these worlds. It is conducting the most sensitive atmospheric analysis in history. It is searching for biosignatures. A biosignature is a combination of gases that shouldn't be there unless life is keeping them there. For example, oxygen is a highly reactive gas. If you left oxygen alone on a planet with rock and methane, it would react and disappear quickly. It would rust the planet. The fact that Earth's atmosphere is 21% oxygen is only possible because plants and bacteria are constantly replenishing it. If we found a planet with both oxygen and methane in its atmosphere, a state of chemical disequilibrium, it would be the strongest evidence yet for extraterrestrial life. It would mean the planet is breathing. If we were to find such a signal, it would fundamentally transform our understanding of reality. It would mean that the chemical alchemy we discussed, the forging of elements in supernovae, the mixing of water and carbon leads inevitably to life, not just here, but everywhere. It would mean the universe is teeming with observers. But there is another possibility. We might look at TRAPPIST-1 and Proxima Centauri and all the other nearby stars and find nothing. We might find that they are all barren rocks, stripped of their atmospheres by the violent flares of their parent stars. If that is the case, the conclusion is equally profound. It would mean that life is incredibly rare. It would mean that the chain of events that led to us, the specific supernova that seeded our cloud, the specific impact that formed our moon and stabilized our axis, the specific location in the galaxy was a miraculous roll of the dice. This brings us back to the fundamental connection between the stars, the deep future, and ourselves. We started this journey with Betelgeuse, a dying giant that will one day seed the galaxy with new elements. We looked at the mechanics of black holes, the engines of gravity that shape galaxies. We explored the violent collisions of neutron stars that created the gold in our electronics and the heavy metals in our crust. And we acknowledged the invisible dark matter that holds it all together. The story of the universe is a story of evolution. It evolves from energy to matter, from simple hydrogen to complex heavy metals, from chaos to structure, and finally, to life and consciousness. We are the thinking part of the universe, the atoms in your brain that allow you to understand the concept of a black hole were forged in the fiery death of a star billions of years ago. The iron that anchors your blood and carries oxygen to your cells was created in the shock wave of a supernova. The hydrogen in the water of your body is as old as the Big Bang itself. We are not separate from the universe. We are not merely inhabitants living in it, like tenants in a house. We are a part of it. We are the mechanism by which the universe knows itself. We are stardust that has learned to sit up, look around, and ask, where did I come from? When you walk outside tonight and look up at the night sky, you are not looking at a foreign, hostile environment. You are looking at your family tree. You are looking at your origins. You are looking at the past that created you and the future that awaits the matter that makes you. The universe is vast, violent, and filled with mysteries like dark energy and the event horizons of black holes. It is governed by laws that defy our intuition and operates on scales that dwarf our entire civilization. But it is also accessible through science, logic, and observation. We can understand it. The story of the universe is still being written, and for this brief, beautiful moment in the Stelliferous era, before the long dark sets in, we are the ones holding the pen. The only thing left to do is to keep watching, keep questioning, and keep looking up.